Imagine for a moment you are in two places at once. Not merely in a metaphorical sense, but physically, tangibly occupying two separate points in space simultaneously. This isn't the opening line to a science fiction novel. It's a fundamental principle in the world of quantum mechanics known as superposition. Concepts like this defy our everyday experiences and challenge the very fabric of our comprehension of physics. Quantum mechanics is not just a branch of physics. It's an invitation to explore the boundaries of reality. In this essay, we will unravel the enigmatic threads of quantum mechanics. From the bewildering principle of superposition, through the spooky realms of entanglement, to the seemingly impossible phenomenon of quantum tunneling, we will explore how these quantum phenomena not only confound our classical understanding of how the world works, but also open doors to incredible technological advancements. Quantum entanglement occurs when pairs or groups of particles interact in ways such that the state of each particle cannot be described independently of the others, no matter the distance separating them. Albert Einstein famously critiqued this idea as spooky action at a distance. Despite his reservations, numerous experiments have confirmed that entangled particles can instantaneously affect each other, even when separated by vast distances. This phenomenon has practical applications in quantum cryptography and quantum computing, where entangled particles are used to perform tasks that are impossible for classical systems. Quantum tunneling is a phenomenon where particles pass through a barrier that they classically shouldn't be able to overcome. This concept is not just a theoretical curiosity, but has real-world implications, such as in the operation of the sun, where quantum tunneling allows nuclear fusion reactions to occur at lower energies than would otherwise be possible. In technology, tunneling is the principle behind the scanning tunneling microscope, which can image surfaces at the atomic level and certain types of semiconductor devices. One of the most confounding aspects of quantum mechanics is the measurement problem. It posits that the quantum state of a particle is not a definite property, but a spectrum of possibilities until it is measured. This leads to the observer effect, where the act of measurement itself influences the outcome, a concept that challenges the traditional scientific method, where observation is supposed to be passive. Wave-particle duality is a foundational concept in quantum mechanics, asserting that every particle or quantum entity can exhibit both particle-like and wave-like behavior. This duality was first brought to light by experiments showing that light, which was previously thought to behave solely as a wave, could also exhibit properties typical of particles. This dual behavior has been observed with electrons and other subatomic particles, fundamentally altering our understanding of the nature of matter and energy. The uncertainty principle, formulated by Werner Heisenberg, states that it is impossible to simultaneously know both the position and the velocity of a particle with absolute precision. The more accurately we know one of these values, the less accurately we can know the other. This principle challenges the deterministic nature of classical physics and has profound implications for our understanding of the universe, suggesting a fundamental limit to what can be known. The strange rules of quantum mechanics have found applications far beyond theoretical physics, influencing diverse fields such as computer science, materials science, and medicine. Quantum effects are exploited in technologies like MRI machines, which use nuclear magnetic resonance to image the human body, and in the development of extremely secure quantum encryption methods for transmitting information. Looking ahead, quantum technology promises to revolutionize numerous aspects of our lives, from ultra-fast computing to ultra-precise timekeeping and navigation systems. Quantum computing represents a radical break from classical computing. Instead of bits, which process data as zeros or ones, quantum computers use qubits that can represent and store information in both zeros and ones simultaneously, thanks to superposition. This allows them to process massive amounts of data at unprecedented speeds. The potential applications for quantum computing are vast, including solving complex medical, environmental, and logistical problems that are currently beyond the reach of classical computers. Quantum mechanics is not just a scientific theory, but a philosophical puzzle. It forces us to question the very nature of reality, what it means to observe something, and whether the universe behaves deterministically. The theory opens up discussions about free will, the nature of knowledge, and the limits of human understanding. These questions are not merely academic. They resonate through many aspects of human thought and existence. While quantum mechanics provides a framework for understanding the universe at the smallest scales, general relativity explains the cosmos at the largest scales, including the behavior of stars, galaxies, and gravity. However, these two theories are currently incompatible, a major puzzle in modern physics. Efforts to integrate quantum mechanics with general relativity into a unified theory of quantum gravity are ongoing, with theories like string theory and loop quantum gravity being leading candidates. The future of quantum physics is as uncertain and exciting as the particles it studies. With advancements in technology and theoretical understanding, the next few decades could see the resolution of long-standing puzzles and the emergence of new, even more complex questions. As young scientists enter the field with fresh perspectives and new experimental tools, the journey into the quantum world is likely to bring us closer to understanding the deepest mysteries of the universe. Quantum mechanics is a fascinating and complex domain of modern science, challenging our classical views of reality and opening up a myriad of technological possibilities. Through this journey into the quantum world, we have seen how it touches on every aspect of our lives, from the devices we use to fundamental questions about the universe and our place within it. As we continue to explore, question, and test the limits of this theory, one thing remains clear. The quantum world will keep challenging us, inspiring us, and most importantly, changing the way we think about the universe.